This is a lecture about the topic of optimal funding of a liability. It's based on the paper by Professor Lesław Gajek of Technical University of Łódź in Poland and myself, which appeared in Journal of Insurance Issues in 2001, number 24, volume 1 and 2. The two volumes are combined, pages 1729. And the purpose is to present the result to you and to discuss some examples. So let's look at the abstract. Funding of a given set of cash flow liabilities is typically arranged through level premium or a single premium. That's a standard actuarial problem. How do we pay for something? Life insurance is paid for typically level annual premium, for example. The question of optimality of the stream of premium payments has been largely ignored in the existing insurance literature, although if you ask employers who pay for pension plans, which is really the most applicable context of this, it is a very important question for employers. Employers generally desire that cost of pension plan stays a level percent of wages that they pay, and the total amount of those wages is typically called taxable payroll, or the total payroll amount, taxable payroll because you also pay taxes on it. And employers don't like it if the amount they have to pay varies a lot, and they would like to minimize the cost if possible. In this work, we propose a set of natural constraints on the premium flows, the payments that we make for liabilities. What are the natural constraints on those? What kind of payments are reasonable? That's basically what we ask. And develop an optimal premium structure to fund any existing liability structure. The result shows how the least costly and actuarially sound funding method, from the perspective of the insured or some more general paying agent, can be developed. So from the perspective of somebody who pays for insurance or a pension plan. The solution applies to either long-term or short-term models, but relies on deterministic assumptions and thus is more likely to be applicable for shorter-term liabilities because they're more predictable, or those long-term liabilities whose cash flows can be determined with great certainty. And that actually is applicable to certain pension plans, because in a pension plan, if you have a large enough group, then the structure of the payouts for retirement benefits is quite deterministic. If you have a lot of people, it basically follows the mortality table, if you have the right mortality table. But there are special mortality tables created for groups of retired people. In a simple, just accounting context, it has been often argued that when paying for a future liability, one should spread the payments over time because this lowers risk. And requiring an employer, for example, to make a sudden large payment could push that employer into bankruptcy, a very undesirable result. Let's examine the premise behind this belief. Assume that we consider a payment for the future liability to be a random game in which the objective is to have the P equal to the expected value of X, where X is a random variable describing the outcome of the game. In this game, the risk can be described by its variance. Now suppose that instead we play n independent games with each played for the 1/n of the previous amount. Then the expected outcome of the game is still E of X, but its variance is lower to 1 over n times variance of X, so significantly lowering the risk. So this is a way to show the logic behind the accounting perspective. However, such an approach does not ask what pattern of payment, whether level payments or some other arrangement, is optimal. That's our question. That's the question of this paper. And it turns out that there is a very reasonable and relatively simple solution for this very common problem of paying for something large that you need to pay for in the future. We will consider some payments that we need to make in the future. in this setup that we have, we'll assume for now that all cash flows are deterministic and subject to a force of interest function, delta sub t, where t is greater than or equal to 0. We don't assume that the interest rate is constant. It may vary by maturity. We'll also assume that all cash flows occur in a finite time horizon within a time interval from 0 to capital T. We assume liability, possibly including expenses, cash flows C sub t occur at discrete times t equal to 1, 2, 3, and so on through t, and some of the values could be 0. And you may say, well, what if these can't be ordered so nicely? And the answer is, well, in the real financial world, yes, they can, because these could be just days. All transactions are settled daily, and basically you can count time in days, and you have to make a payment within a certain day. So it does work like this in the real world. The present values are L sub t equal to C sub t times e to the minus the integral from 0 to t of the force of interest. So basically the present value factor is established by this possibly varying in force of interest, but we calculate these present values directly using the standard formula, applying the force of interest and taking that e to the minus integral of the force of interest. And that becomes the discount factor, the present value factor. And let us also denote the present value at time 0 of liabilities accrued through time t by AL sub t. So it's a sum of all these present values of payments that are made through time t. Everything that is due to be paid up to time t, but we take the present values of those, add them up, and we look at them at time 0, and that's what we need to pay for, although we need to pay for eventually for all of them through the end, through the last time, which is big T. We also define AL0 equal to 0. So that we assume that all the liabilities to be paid are in the future, because what's the point of figuring out how to pay for things that we pay right now? The liabilities as defined here are to be funded through payment of a series of premiums, P sub t, indexed by times, the same times as the liabilities. And of course these payments could possibly be 0. And to follow the industry practice, we assume throughout the paper that the premiums are paid at the beginning of each time interval, because insurance premiums are paid at the beginning of the period and the benefit is paid sometime later. But we will assume the premium paid at time t minus 1 with time t, we will index the payments with the something like policy year. So first year premium P1 is paid at time 0, second year premium P2 is paid at time 1, and so on. The present value of PT is P sub t times e to the minus integral from 0 to t minus 1 delta sub s ds, because, as we said, the payment is made at the beginning of the period indexed with number t. We'll also denote the present value of premiums paid through time t, but before it by AP sub t, and it's a sum from I equal 1 to t of the present value of pi. And note that this is the present value at time 0, so we bring all the liabilities values to time 0 and all the premium values to time 0, and we consider accrued liabilities through time t and accrued liabilities and accrued premiums through time t. Well, as the title of this paper and everything that I've said before indicated, the goal is to determine an optimal pattern for the premium payment flow. Determination of a proper method of funding of existing liabilities may indeed be considered to be at the very heart of the job of an actuary. That's what we do as actuaries. We figure out how much we should pay for things and how we should pay for them if they're uncertain and in the future. In this case, the payments are certain. We know what they're going to be. So you may wonder what's the big deal, but the big deal is that there are numerous payments in the future. They're spread over time. We're trying to figure out how to pay for them. And of course, we could just wait until they come due and make the payment then. But that's not very actuarial, because that means that if there's any trouble on the way, we may end up without having any money to make the payment when it comes due. So one could choose a non-actuarial approach and postpone funding indefinitely into the future while generating cash by creation of new liabilities. So you basically tell people, let me handle this money for you and I'll pay for something for you in the future. That's what politicians do a lot. And we call this in this paper the Luci funding method, after Lucille Ball, who in one of episodes of I Love Lucy had a conversation over the phone with a banker, and the banker was saying something and she was visibly upset, and she said, well, I can't be overdrawn. I still have some checks left. So she was hoping to borrow the money until, well, sometime in the future she would make the payment. And the banker was just supposed to cover it, and eventually she'll pay back. It's no problem. We see that a lot, but it's not the best approach, and actuaries generally do not approve of it. Or we could choose the other extreme of a single payment, P, made at time 0. Well, just try to tell an employer, okay, well, you have all these workers, you promise them pension benefits, just pay up. Pay this $10 billion right now. That will take care of it. We'll invest it and disperse the funds eventually. And then there is the traditional approach of level premiums. That's very common. Life insurance is paid with level premiums, so nothing unusual about that. Instead, we postulate the following criteria of optimality of the funding method. So we'll postulate the criteria. I'll ask you to think about them and decide if these are good criteria, but we definitely think these are very good criteria. Here is the constraint, really, that we put on the method of payment. Constraint 1. The present value of premiums, P of P of T, is a non-increasing function of time. So present value of PT is greater than or equal to present value of P of T plus 1. In other words, you can't really push the payments into the future. You have to pay something all the time, and the payments in terms of their present value at time 0 can't be increasing, because that's the standard method of pushing things into the future. You don't pay anything now, and you really promise you'll pay later. That's something that we don't want, because that's really the way that things get messed up. If actuaries are ignored, actuaries always want to prepay for things, and then eventually in the future it turns out that the liabilities have accumulated to be so large you can't afford to make even a one payment. So we don't want this to happen. We need people to prudently accumulate funds to make the payments as they come due. This is, in our opinion, the key to the funding method meeting the test of actuarial prudence. While postponing of funding is allowed, premiums can, at most, be level in terms of their present values. Clearly, level funding, even at 0 interest rate, meets this test. So does a single premium paid at time t equal to 0, because the actual future payments now are much lower than the current payments. On the other hand, the Luci funding method of just postponing payment and borrowing money if necessary, but not paying anything until whatever, whenever, at infinity, that fails this critical test. Here's constraint 2, the second constraint that we impose as necessary for a funding method to be sound. Accrued premiums at any point in time exceed accrued liabilities payable through that point in time. So AP sub t is greater than or equal to AL sub t for t equal to 1, 2, and so on through t. And eventually AP sub t, capital T, is equal to AL capital T. In other words, all liabilities are paid for with the premiums that we have completely, and at any point in time, the premiums accrued through that point in time are enough to pay the liabilities accrued through that point in time. And effectively this means you never borrow money in order to make the payments. So this means in actuarial terms that the reserve is non-negative at any time, and the liabilities are fully paid off at the end of the time horizon, while premiums are used solely for the purpose of fully discharging the liabilities. This does not necessarily imply that these are net premiums, as we possibly allow for inclusion of expenses and cost of capital among liabilities cash flows in this model in general. Let us observe that if we were to replace inequality constraint 1 by equality, this would generally lead to a contradiction with constraint 2. So we don't allow the premiums to increase, but we don't require the present value of the premium for every time to be exactly the same at time 0. So basically we don't enforce level premium, and if we want a non-negative reserve, the liabilities could be of complicated structure, and we may not be able to get what we want. So the non-increasing premiums, condition 1, can't be really easily replaced by insisting that the present values of all the premiums must be equal. Under these two constraints, we seek to minimize AP sub t minus AL sub t for t equal to 1, 2, 3, and so on through t. And note that we do not seek to minimize a single quantity, but rather to simultaneously minimize all possible, and these quantities are basically reserves, because what is a reserve in any form of life insurance or long-term insurance? It's the accumulated actuarial value of premiums through time t minus accumulated actuarial value of benefits and expenses through time t. So in this case, accrued premiums minus accrued liabilities through time t. That's the same idea. So we simultaneously minimize all possible reserves by choosing one of all possible sets of premiums, meeting constraints 1 and 2. And we hope that we can find this, but it's ambitious, but hopefully it will work. This minimization condition effectively calls for the smallest possible reserves throughout the existence of the policy, subject to constraint 1 calling for not delaying the funding into the future, or not delaying it excessively, and condition 2, or constraint 2, calling for proper reserving. So you don't have negative reserve, you don't borrow money to make the payments. In other words, we seek to minimize the cost of funding while remaining actuarially sound. This addresses the needs of both the insured and the insurance firm. And guess what? There is actually a solution. So let us write f for a real-valued piecewise linear continuous function defined on 0 to t, such that f of 0 equals 0. And such a function, because it's piecewise linear, it's absolutely continuous and differentiable with a derivative f everywhere except for a finite number of points where f is not well defined, because we defined it to be piecewise linear. We can extend the derivative of big F, little f, on 0t by assuming it to be equal to 0 at 0 and to be continuous from the left-hand side at every other point, thus uniquely defining the derivative of f continuous from the left-hand side. and then the big F will be the integral of little f. And that's just a purely theoretical construct at this point, but we'll use it to say something important in just a moment. And now let's make it more specific. Let this big F be AL sub t. This is defined at all integer values of t in the interval from 0 to capital T. I say, well, the text says integral values. That's actually an adjective that refers to integer values. Then f is a function of time representing present value of liabilities, for example, pension liabilities, accrued through time t. And let us extend its definition to all t from 0 to t by making it piecewise linear and continuous with a number of non-differentiability points as small as possible. And this is kind of a fancy way of saying that if you can continue through a point in a straight line, then it will be differentiable there. But otherwise, just connect the dots into a piecewise linear function. And then, for that big F, let f star be the smallest concave majorant of f. So f star is the smallest real valued function defined on 0t such that f star is concave, and f star of t is greater than or equal to f of t for all t between from 0 to t, 0 to capital T. It is clear that f star could be defined as the smallest concave majorant for the function f1 of t equal to alt at all integer values or integral values of t, and 0 otherwise on 0t. It would be the same thing because we want it to be continuous and concave. Let little f star be the continuous from the left-hand side derivative of f star. We defined f star of 0 to be 0 by definition. Then the premium pt star minimizes apt minus L of t for all t among all possible premiums satisfying constraints 1 and 2, if and only if the present value of pt star is equal to f star of t. In other words, the present values of the premiums have to be equal to the values of this derivative of the smallest concave majorant function at every integer point from 1 to t. That's the solution. So what you do is you draw a piecewise linear continuous function over all points where AL of t, AL sub t is defined. Okay, so you have all these dots where it's defined at integer points, connect them with straight lines, and then over it put a function that is greater than or equal to it, but the smallest possible, which is concave. So anytime the underlying ALT causes these lines that should draw them to behave in a convex way, so that the next line over has higher slope than the previous line, starts going up faster like an exponential function, all you do is just replace the two lines by one straight line going over them, which remains straight while they have that point where their derivatives are different. So you put a straight line on top of the lines that are not concave. Well, okay, that's very nice, but can we prove this? And the answer is yes, we can. Let's prove it. First, let us consider an arbitrary premium flow that meets constraints 1 and 2 and minimizes APT minus ALT for all t, little t. Because present value of P of t is a non-increasing function of t, the piecewise linear continuous function f star, defined by interpolating linearly the relationship t going to APT to all t for all t between 0 and t is concave. Constraint 2 implies that f star of t is greater than or equal to f of t, where f of t is ALT. Because AP minus ALT is minimized, well, that means this is a majorant, which is concave, and because the difference is minimized, it is the smallest concave majorant. So yes, anything that is optimal has to be that smallest concave majorant. On the other hand, if f star is the smallest concave majorant for f of t equal to ALT, defined at all integral values of t, so integer values of t, and then extended to all t between 0 and t, then f star satisfies constraint 1 because it's a majorant, and constraint 2 because it is concave. And it minimizes all APT minus ALT for t equal to 1 to t because it is the smallest among concave majorants. And here is the figure that illustrates this. So let's think carefully about this. We have liability payments that come at this time here, and this vertical line represents the present value of the first liability payment. Then their second payment, which has this present value, comes here, and we put this line on top of the first line because we're looking at accrued liabilities at each point. So this point at the top is the total of the two in terms of the present value. Then the next one here and the next one here. And what is happening here is that we first look at the function that just connects the dots starting at 0, 0, goes to the first point here, the second one here, then here, and then here. And this is kind of a function that describes the accrued liability. We create a continuous piecewise linear function from them. That was the very first thing that I started with. But we look for a function that would lie on top of it and be concave. Never do this thing that would have a line going up and then another line going up faster so that there's a convexity here. No convexity. You can go up but not faster, and then you can go up more slowly because that creates concavity. So on top of that previous function we put this piecewise linear function, which is the smallest concave majorant. That's this line and this line here. And then we take the derivative, which is really the slope of this line over here and the slope of this line over here. And every year the payment of the premium has the present value equal to the slope of the line. That's the optimal payment. That will take care of the whole problem. The premium flow defined here has one more important optimality property within the class of all premium flows P1 through Pt that satisfy constraints 1 and 2, and also have the property that AP big T is equal to AL big T. So premiums are used solely to fully discharge the liabilities. Premiums P1 star through Pt star determined by the derivative of the smallest concave majorant give the minimum value of square error measure, which is the sum from t equal 1 to t of q minus q sub t squared, where q sub t is the present value of the premium at time 0, and q is the level funding in the present value form. So basically all payments of liabilities averaged out, how much would it cost on average per year. So basically we are the closest possible in terms of the mean square error measure to level funding, but not exactly that because we must satisfy constraints 1 and 2 first and foremost. Now if you read the paper that is provided in RegiNet for the class, you'll see a proof of this, but I don't test you on the proof of this. This is just an interesting exercise The only thing that I ask you to know is to know this optimal funding method. There will be possibly questions on your tests about this optimal funding method. That's what you need to know. And here's the first exercise on this optimal funding method for you. Mr. Romanov, who is 25 years old, is planning for retirement, and in order to provide for it, he estimates that he will need 2,200,000 monetary units at age 65, adjusted for inflation, so in terms of today's purchasing power. He does not have any current savings. His daughter Anastasia was just born, and Mr. Romanov also plans to provide for her college education, which will cost 180,000 monetary units when she turns 18, also in terms of today's purchasing power. Mr. Romanov invests conservatively in securities with rates of return matching the rate of inflation. Calculate the optimal annual savings amount that Mr. Romanov should invest every year at the beginning of the year to fund his liabilities in an optimal fashion. And here's the solution. So because he earns the rate of return which matches the rate of inflation, he will effectively earn 0% real return on his savings, and for all funds, present value equals future value in terms of purchasing power. We can use the smallest concave major end fund in order to find the optimal funding with the following future liabilities: 2,200,000 in 40 years and 180,000 in 18 years. The linear function connecting the point 0,0 and the point 18 and 180,000 has the slope 180,000 minus 0 over 18 minus 0, so it's 10,000. The linear function connecting the point 18 and 180,000 and the point 40, 2,380,000, where 2,380,000 is equal to 180,000 plus 2,200,000, that's because we take the accrued liabilities. It has the slope of 2,200,000 divided by 22, and that's 100,000. Since the second slope is higher, the smallest concave major end will require the level funding of the terminal amount of 2,380,000 over 40 years, so 59,500 per year, or about 4,058.33 per month. That's the optimal funding for this case. Here's another exercise. This is basically a change in the assumptions of the previous exercise. Assume now that Mr. Romanov has decided instead to invest in stocks earning an annual real, after inflation, rate of return of 7% per year. How will this change his optimal funding structure? And here's the solution. So we can use the smallest concave major end methodology again, but in this case we should work with all liabilities and funding amounts being expressed as present values at 7%. Mr. Romanov's retirement funding requires 2,200,000, but discounted at 7% over 40 years, and that's 146,916.84 in terms of present value at time 0. Well, Anastasia Romanov's college education funding requires 180,000 discounted at 7% over 80 years, so that's 53,255.50 in today's purchasing power. The slope of the line connecting the point 0,0 and 18 and 53,255.50 is 2958.64. While the slope of the line connecting the point 18 and 53,255.50 and the point 40 and 200,172.34, where 200,172.34 is the sum of 53,255.50 and 146,916.84. So that slope is 6678.04. That's just the increase, really, the increment of this 146,916.84 over the increment in years, which is 22 years. Therefore, level funding of the amount of 200,172.34 over 40 years, or 5,004.31 a year in terms of today's present value, is called for, because this slope is significantly higher than what we got before, which was just under 3,000. So the cost of retirement is still much higher than the cost of college in terms of relative slopes there. And so we go for funding the total, basically funding college on the way to retirement. So the optimal funding is in year 1, 5,004.31, then increased by 7 years, but by 7%, because everything assumes 7% return, and so on. And year 4 funding would be equal to 70,034.40. It should be noted that the total savings at the end of year 18, when Anastasia heads for college, will be 304,456.03, significantly in excess of the college funding needs, indicating the simultaneous funding of retirement achieved while saving for college. And one more exercise. Now assume that Mr. Romanov is willing to take a very high level of risk and as a result will earn substantially higher rate of return. How high will that rate of return have to be so that Mr. Romanov does not save for retirement while saving for the cost of college education of Anastasia Romanov? So he first saves for retirement, for college, and then for retirement. And here's a solution. The situation desired will require that the smallest concave major end should be just a straight line, so that these points 0, 0, 18, and 180,000 discounted at the rate of interest I over 18 years, and then 40 and 180,000 discounted over 18 years, plus 2,200,000 discounted at over 40 years at the rate of interest rate. This is a straight line. This implies that both lines must have the same slope, and we write out those slopes and set them equal to each other. And this, after some calculations, becomes the equation that 10,000 over 1 plus I to the 18th has to be equal to 100,000 over 1 plus I to the 40th. And that implies that 1 plus I to the 22nd is 10, and I is approximately equal to 11.03%. Here's another exercise. Mr. Louis Bourbon is a king of a Western European country plagued by high levels of poverty among its elderly population. Mr. Bourbon proposes to introduce a flat benefit paid in gold to the elderly aged 65 and above, paid commencing on the 65th birthday of each citizen until death of the citizen. The benefit will be funded by general revenue budget, so by all taxes levied by the kingdom, not by special taxes allocated to this program. Because of recent expenditures of support of War of Independence for major competing powers overseas colonies, Mr. Bourbon is concerned about the cost of the program and would like to minimize the expenditures while not being forced to borrow to finance the program. All payments will be made in gold, which earns 0% real rate of return, so it exactly retains its purchasing power. Mr. Bourbon estimates that the total benefit payment cost will be 100,000 gold coins the first year, 200,000 gold coins the second year, 300,000 gold coins the third year, and then 500,000 gold coins for 7 years, and after that 400,000 every year forever. Calculate the optimal funding for this retirement scheme designed by Mr. Louis Bourbon. And here's the solution. Since all payments are in gold, and gold is assumed to neither appreciate nor depreciate in purchasing power, we can take all amounts as present values. The optimal funding is determined by the smallest concave matrix. The slope of the line connecting the two initial points, 0, 0 and 100,000 is 100,000, while the slope of the line connecting 0, 0 and 2 and 300,000 is 150,000. Thus, year 2 payment will need to be pre-funded. So basically take the 2 years together. The slope of the line connecting 0, 0 and 3, 600,000 is 200,000. So year 3 payment will also need to be pre-funded. The slope of the line connecting the point 0, 0 and 4 and million 100,000 is 275,000, and as this is greater than 200,000, indicating further pre-funding need. I should say this is greater, but since the funding needs following year 4 are 500,000 every year, they are always bigger than the funding needs in the first 3 years, and we should find the slope of the line connecting point 0, 0 and 10, 4,100,000, which is 410,000, and this indicates the optimal funding level for the first 10 years. The optimal funding for the years beyond the 10th year is the constant 400,000 liability payment the same year.